of earthquake, magnitude versus intensity. I am Kathleen May Araclan, and I will give you some introduction to our topic, followed by Joyce Ann Lalucine about the determination of hypocenter or earthquake focus, then Charles Vincent Escal and Aldrin Motas for the sizes of earthquakes, and concluded by Evian Cepilio. So for our introduction, I will be discussing about what is earthquake. So earthquake means the shaking of the earth's surface. It is a sudden trembling of the surface of the earth. And earthquakes can certainly a terrible natural disaster. Yes, of course, ang isang earthquake ay disastrous or meron siyang tendency na makadamage to our life and property. Kasi nga, ang isang earthquake is unexpected to come. So, meron tayong chances na hindi makapaghanda pero meron tayong mga prevention kung anong gagawin natin during an earthquake. So, the best thing that we can do is to know what is it and to protect ourselves kapag nagkakaroon ng unexpected earthquakes. So, some earthquakes are weak in nature and probably go unnoticed. Meron tayong tinatawag na mga minor and major earthquakes. For the minor, maaaring maramdaman sa place na to yung lindol but other places are not. For the major earthquakes naman, malakas tong earthquake na to and meron tayong possibility or tendency na maramdaman itong earthquake from other places. Next is, where do earthquakes happens? So, earthquakes usually occur on the edge of the large section of the Earth's crust called tectonic plates. So, these plates slowly move over a long period of time. So, sometimes the edges, which are called fault lines, can get stuck, but the plates keep moving. Pressure slowly to build up where the edge are stuck, and once the pressure gets strong enough, the plate will suddenly move, causing an earthquake. So, ang earthquakes, it can be, yung mga plate boundary nila is about divergent, magda-diverge, or convergent, and nagko-converge. So, yung movement ng ating mga plates is nagko-cause ng earthquake. Next is, can scientists predict earthquakes? So, unfortunately, scientists cannot predict earthquakes. Unlike the typhoon or yung mga bagyo natin na monitor natin kung kailan sila dadating because of the satellite. But these earthquakes cannot be. Because earthquakes are usually come kapag calm lang, usually wala namang masyadong sign about earthquakes unless nagkaroon ng volcanic eruption. So, the best way that the scientists can do is to point out kung saan nagkaroon ng earthquake, yung epicenter niya mismo, at kung saan siya nag-occur. So, that is the scientist can do. Kasama rin sila ng mga seismologists. Next is the anatomy of an earthquake or yung mga earthquake terminologies natin. So, meron tayo diyang fault, epicenter, hypocenter, plates, and the seismic waves. So, the motion of plates result in stress build-up along plate boundaries as well as in interior domain of the plate, depending on the state of build-up of stress and the amount of resistance offered by the fault. Rupture is initiated as stress exceeds the capacity of the strata. So generally, the rupture causing earthquakes initiate from a point termed as hypocenter or focus, which subsequently spreads over a large area. So, ang ating hypocenter, this is the place where the earthquake starts. It is below the Earth's surface. So, nasa ilalim siya nag-start, yung ating hypocenter or yung focus. And then, depending on the characteristics of strata where rupture occurs, the shape of the ruptured area could be highly irregular, and the amount of interface slip along the ruptured surface could also vary. Next naman natin is yung place of origin, which is also known nga as our focus, origin center, or hypocenter. Yun namang tinatawag natin na epicenter. This is the place directly above the focus, or this is where the earthquake is very strong. It is the point where the earthquake is more strongest, kung saan mas nararamdaman natin talaga yung isang lindol. So, example ng isang epicenter ay sa specific area which is Panay Island. So, mas makikita natin doon na ang maire-report sa news or sa PHIVOX that the epicenter was located at 11.34 degree north, latitude 122.10 degree east longitude. And it is having the vicinity of Colasi Antique. Pero siya ay nasa Panay Island. So, ito yung parang pinaka-specific talaga, yung epicenter. Malalaman natin kung ano yung mga details in numbers and also yung parang pinaka-vicinity talaga niya in Panay. So, malalaman natin, example, lumindol sa Panay. So, saan mismo dun sa Panay? Yun yung tinatawag natin na epicenter, yung binanggit ko kanina. So, for obvious reason, the destruction caused by the earthquake at this place will always be the maximum. Yun nga, dun sa epicenter. And with an increasing distance from this point, the intensity of destruction also decreases. So, paglayo, pagbaba ng nafe-feel na lindol. So, the point on Earth's surface diametrically opposite to the epicenter is called the anti-center. So, again, yung mga seismic waves, yun yung mga naglalakbay na nararamdaman natin na lindol. So, paglayo natin sa pinaka-epicenter, pagbaba, and paglapit, paglakas ng isang lindol. Next is the Recording Earthquakes by Mercalli 2005. The vibratory motion produced during an earthquake could be measured in terms of displacement, the final point minus the initial point, velocity or acceleration. So the one who is very interested in even small amplitude of ground motion and also provide insights on the wave propagation characteristics are the seismologists. So they give them or enables them to estimate the associated earthquake parameters. For us, acceleration are the causative phenomena for forces that damage structures. So we have the force is equals to mass times acceleration. And the engineers are more concerned with that because of the earthquake is causing structural damage to the infrastructures. So, ang mga engineers, inaalam nila yan for them to know kung paano nila patitibayan ng isang building or structures and infrastructures na binibuild nila. So, they are very interested in acceleration measurements. Next is the instrument that measures the ground displacement are called the seismographs, and the record obtained from the seismograph are the seismogram. And this is an example of a typical seismograph on how to record an earthquake. So in a seismograph, we have a magnet, string, pen, pendulum, rotating drum, and a chart paper. On the second picture, we can see the actual recording of a seismograph or yung itsura niya kapag ka nagkakaroon ng lindol. Meron tayong malalaki ditong haba which is means na merong major earthquake na naganap. And sa pagliit niyan and pagwala ng mga waves is paghina ng isang earthquake. For the third picture is the front view na makikita natin na ganito lang ang isang seismograph. But it is very useful in determining the magnitude of an earthquake. So the seismograph has three components, that is the sensor, recorder, and the timer. So the principle on which it works is very simple and explicitly reflected in the early seismograph. So we have a pen attached at the tip of an oscillating simple pendulum and marks on a chart paper that held on a drum rotating at a constant speed. We have also a magnet around the string that provides required damping to control the amplitude of oscillation. So, yung three components ng isang seismograph is very important. Kasi, ang sensor ang nakaka-sense if there is a earthquake. So, gumagamit tayo ng mga pendulum mass, string, and magnet. So, yung tatlong yan ay indicated as our sensor. For our recorder naman, na nagkikip ng mga details and info about the earthquake, we have the drum, the pen, and the chart paper para makita ang lakas ng isang earthquake. And the motor that rotates the drum at a constant speed forms the timer. Dito naman, ang isang timer is kung gaano katagal ang isang earthquake. So, pag nagre-record, nagro-rotate yung ating rotating drum. So, sa start na nagkaroon ng malaking line sa ating chart paper, doon mag-i-start ang time. And kung saan lumiit na or umipis, nung lumipis na yung line, doon na yung pagbaba or paghina ng isang lindol. So, doon natin makikita yung duration ng isang lindol. By varying characteristic of equipment, one could record displacement, velocity, or acceleration during an earthquake. So, this seismograph is very important in recording an earthquake and also its three components.
Energy of an earthquake. Earthquakes create several distinct types of wave with different velocities. With this, are measured at seismic observatories. Their different travel times help scientists to locate the source of the earthquake. Yun nga, nagkakreate ang earthquake ng different seismic waves na kung saan may iba't iba ding speed at mag-a-arrive at a seismic location at different times. Para kasi sa mga scientists, mas madali na madadetermine kung gaano kabilis ang waves na nag-travel. From that observation kasi, by measuring the time takes for seismic waves to the travel in any directions through the Earth, mas mafi-figure out yung velocity structure of Earth. When an earthquake occurs, the fault movement generates seismic waves of energy that spread outwards through the ground in all directions simultaneously. An approximately relationship between surface wave magnitude and the energy released by an earthquake is given by log E is equals to 4.8 plus 1.5 m. Once the magnitude of an earthquake is determined, the amount of energy released as waves, the ratio of energy released by two earthquakes differing by 1 is magnitude is equal to 31.6, and the ratio is 1,000 for earthquakes differing by 2 in magnitude. Table 1.2 increase in energy release for various range of increase in value of magnitude. Dito natin makikita yung comparisons have been made between natural forces and nuclear weapons. The energy released by 1 megaton hydrogen bomb is roughly equivalent to a magnitude 7.4 earthquake.
We know that earthquakes cause tremors on the earth. The tremors produce waves on the surface of the earth. These are called seismic waves. Seismic waves are recorded by an instrument called the seismograph. The instrument is simply a vibrating rod or a pendulum. which starts vibrating when tremors occur. A pen or a marker is attached to the vibrating system. The pen records the seismic waves on a paper which moves under it. Trigger a mock earthquake on the table to see the seismograph in action. We can see that the pendulum tip records the earthquake on a graph sheet. In this activity, we have seen the recording of seismic waves caused by earthquakes.
Energy of an earthquake. Earthquakes create several distinct types of wave with different velocities. When these are measured at seismic observatories, their different travel times help scientists to locate the source of earthquake. Yun nga, nagka-create ang earthquakes ng different seismic waves na kung saan may iba't iba ding speed at mag-a-arrive ito in any seismic location at different times. Para kasi sa mga scientists, mas madali na madedetermine kung gaano kabilis ang waves na nag-travel. From that observation, by measuring the time takes for seismic waves to travel in any directions through the Earth, mas ma-figure out yung velocity structure ng Earth. An approximately relationship between surface wave magnitude and the energy released by an earthquake is given by lag E is equals to 4.8 plus 1.5 m. E ang energy na na-release and ms naman ang surface wave magnitude. Ginagamit ang formula lag E is equals to 4.8 plus 1.5 m kapag yung magnitude ng earthquake ay na-determine na yung amount ng energy na na-release. Makikita naman sa table ang increase ng magnitude at ang pag-increase ng energy na na-release nito. The ratio of an energy release by two earthquakes differing by 2, earthquakes differing by 1 is magnitude, is equal to 31.6. The ratio is 1,000 for earthquakes differing by 2 in magnitude.
Size of earthquakes. The size of earthquake could be related to the damage caused or parameters like magnitude. These two useful definitions of the size of earthquakes are sometimes confused. Intensity of earthquakes. The intensity of an earthquake refers to the degree of destruction caused by it. In other words, intensity of an earthquake is a measure of severity of the shaking of the ground and its attendant damage. This, of course, is empirical to some extent because the extent of destruction of damage that takes place to a construction at a given place depends on many factors. Some of these factors are: number 1, distance from the epicenter. Number 2, compactness of the underlying ground. Number 3, type of construction. Number 4, magnitude of the earthquake. Number 5, duration of the earthquake. Number 6, depth of the focus. Intensity is the oldest measure of earthquake. The Seismic Intensity Scale. The Seismic Intensity Scale consists of a series of certain key responses such as the people awakening, movement of furniture, damage to chimneys, and finally, a total destruction. Numerous intensity scales have been developed over the last several hundred years to evaluate the effects of earthquakes. The most popular is the modified Mercalli Intensity Scale. This scale, composed of 12 increasing levels of intensity that range from imperceptible shaking to catastrophic destruction, is designated by Roman numerals. Next, the Msk64 Scale. This scale is more comprehensive and describes the intensity of earthquake more precisely. Indian seismic zones were categorized on the basis of the Msk64 scale. It is somewhat similar to the modified Mercalli scale used in the United States. The MSK scale has 12 intensity degrees expressed in Roman numerals to prevent the use of decimals.
Earthquakes are unpredictable, but scientists can estimate how much the ground might shake based on what's going on underneath our feet. Let's take these two examples. Jen here lives on bedrock, and James lives in a large basin where loose dirt and sediment have collected over millions of years. If an earthquake hits, James' home, which sits on unconsolidated or loose sediment, will shake more than the solid rock Jen's house sits on. This also means James will have more damage to his home and neighborhood. The damage and amount of shaking caused by an earthquake can be measured using the Mercalli Intensity Scale. The Mercalli Intensity Scale is subjective and describes the amount of shaking and effects earthquakes have on humans and structures. It has levels from 1 to 10. The scale was developed by Giuseppe Mercalli, a Roman priest and professor of natural sciences around 1900. Scientists still use it to show which areas will see more damage and shaking during an earthquake. It can also be used to help people understand their risks and prepare. It's different from the Richter magnitude scale that also ranges from 1 to 10 and describes how much energy an earthquake releases. Instead, the Mercalli Intensity Scale describes the effects of earthquakes on humans and property. As magnitude increases, intensity does too, but it's not uniform. It all comes back to what's beneath our feet. Depending on what the subsurface is made of, shaking during an earthquake will be felt differently. Next are some descriptions of the types of damage and shaking at different Mercalli intensities. Level 1. Hardly anyone will feel level 1 shaking. Most people won't even notice an earthquake has happened. Level 2 and 3. Only a few people will notice weak shaking, as it will feel similar to a big truck passing by on a busy street. Level 4. Light shaking will wake people up who are sleeping. It will make doors and windows rattle. Level 5. Moderate shaking will cause trees to sway, cups and dishes to shift and break, and doors to swing back and forth. Level 6. Strong shaking will make it hard to walk. Objects will fall off shelves and windows may crack. Level 7. Very strong shaking will cause serious damage in old brick buildings. Plaster and brick chimneys might fall. Drivers will notice the shaking and stop their cars. Level 8. Severe shaking will cause heavy furniture to fall over, homes to shift on their foundations, and cracks to form in the ground. Level 9. Violent shaking will lead to landslides, breaking pipes, and badly damaged homes. Level 10 will cause extreme shaking and widespread destruction. Some bridges will collapse and railways will bend. Power and damaged and non-functioning. Each level of the Mercalli Intensity Scale builds on itself and can help us understand what level of shaking might be felt and the types of damage we might see in different areas. Remember, earthquakes are unpredictable, but scientists have good estimates of which types of earthquakes might happen near you and how much shaking you could see. Check out local resources, learn your risk, make a kit, and get prepared. Thanks for listening.
The Rosi Pharrell scale. It was one of the first seismic scales to represent earthquakes' intensities. It was used commonly for about 2 decades until the introduction of the Mercalli Intensity Scale in 1902. The Jma Intensity Scale. The Japan Meteorological Agency Seismic Intensity Scale, known in Japan as the Shindo Seismic Scale, is a seismic intensity scale used in Japan to categorize the intensity of local ground shaking caused by earthquakes. An imaginary line joining the points of the same intensity of the earthquake is called an isosysmal. In plan, the different isosysmals will appear more or less as concentric circles over a plane homogeneous ground if the focus of the earthquake is a point. Over the years, researchers have tried to develop more quantitative ways for estimating earthquake intensity. One of such relationships correlating earthquake intensity to peak ground velocity is given by this formula where V sub g is the peak ground velocity in centimeter per second. Another such relation reported by Wald et al. In 1999 based on Californian earthquake database is, in addition to peak ground velocity, empirical relationships correlating peak ground acceleration to MMI has also been reported. The magnitude of an earthquake is related to the amount of energy released by the geological rupture causing it. and is therefore a measure of the absolute size of the earthquake without reference distance from the epicenter. While earthquake intensity is depicted in Roman numerals and always a whole number, magnitude is depicted in Arabic numerals and need not be a whole number. Similar to intensity scales, over the years, a number of approaches for measurement of magnitude of an earthquake have come into existence.
There are different kinds of scales used for measuring the magnitude of an earthquake. The first one is the Richter magnitude scale. Richter magnitude scale was developed by Charles Francis Richter. Siya din ang nag-propose ng workable definition of magnitude. He defined that the earthquake magnitude scale, which is denoted by capital letter M, ay equals a logarithm to the base 10 of the amplitude ng pinakamalaking seismic wave na na-record ng seismograph, which is located at 100 kilometers from the focus of an earthquake. Eventually, na-revise ang Richter scale at na-renamed as the local magnitude scale, which is denoted by M sub L. Ang formula naman ng magnitude of an earthquake kung saan ang seismograph ay located more than 100 kilometers from the epicenter of the earthquake ay M is equals to M sub delta minus 1.73 logarithm to the base 10 of 100 over delta, where delta is the distance of the epicenter from the seismograph. The next magnitude scale is the moment magnitude scale, which was developed by Thomas Hanks and Hiro Kanamori. Moment magnitude is based on the seismic moment due to earth rupture. It is about the same as the Richter magnitudes for small to large earthquakes, but only the moment magnitude scale is capable of measuring magnitude 8 and greater events accurately. Ang difference ng way ng pagkuha ng magnitude ng Richter and moment magnitude scale ay ang Richter scale ay nakabase sa intensity of shaking of the ground or the seismic waves, while ang moment magnitude scale naman ay nakabase sa paggalaw ng fault or yung rupture ng fault. Ang Richter's magnitude scale ay nagsasaturate at about 6.8 magnitude, kaya mas accurate ang moment magnitude scale sa pagkuha ng mas malalaking magnitude ng isang earthquake. The formula for the moment magnitude scale is M sub W is equals to 2 over 3 times the quantity of logarithm to the base 10 of M sub O minus 9.1, where M sub W is the moment magnitude and M sub 0 is the seismic moment. Other magnitude scales are the surface wave magnitude, which is denoted by M sub S, that is based on the amplitude of Rayleigh waves having a period of about 20 seconds, while the other is the body wave magnitude, which is denoted by M sub B, that is based on the amplitude of first few P wave cycles. Here in the Philippines, the scale used and developed by PHIVOLCS is the PHIVOLCS Earthquake Intensity Scale, or the PEIS. As you can see on the graph that compares different magnitude scales, yung moment magnitude scale or the black line, yung nakapag-measure ng magnitude 0.9. While yung Richter scale or yung red line ay nakapag-measure lang ng around magnitude 7.
Earthquakes are now reported as moment magnitude. So what happened to the Richter scale? Charles Richter and Benno Gutenberg developed the first magnitude scale in the 1930s to quantify earthquakes by relating the size or amplitude of seismic waves, shown on the right, plotted against distances calculated from S minus P arrival times, shown on the left. Connecting the two gives you the Richter magnitude. The scale is logarithmic, so a 1 unit increase in magnitude corresponds to 10 times larger amplitude. The limitation was that seismologists measured certain frequencies, which meant that the signals from large earthquakes weren't adequately represented, like not being able to hear the bass notes on your laptop speaker. That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allow them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result was the moment magnitude scale. Seismologists no longer look at only the amplitude of seismic waves, but instead use much more information contained in the seismogram to calculate what is called the seismic moment. The seismic moment, which defines how much force is needed to generate the recorded waves, is defined by this equation: mu times distance times area. Mu is rock rigidity. It describes the resistance of the rock to bending when force is applied and is a constant for a given rock material. More elastic energy is stored bending rocks of high rigidity than is stored bending rocks of low rigidity. For example, this brick has high rigidity and when bent or sheared would yield a strong earthquake. The cake has lower mu and shears easily. Rock rigidity is lower in the crust than it is in the mantle. As mentioned earlier, in most cases, distance and area can be determined by mathematical modeling of seismograms. D is the distance that the rock slipped along one side of the fault zone relative to the other side. In the 1906 San Francisco earthquake, this fence line was offset over 3 meters. A is the estimated area of the fault zone along which the rock slipped, the distance D. It defines the area that actually ruptured during the earthquake. Let's watch an earthquake happen. The arrows show forces building on opposing sides of a fault. Growing stress that will be relieved in the earthquake will be shown in red. Here we see blocks of rock move in opposite directions along a strike-slip fault zone, such as the San Andreas Fault in California. Potential energy, in the form of elastic energy, is stored in Earth's crust or mantle, building stress as the ground slowly deforms between large earthquakes. Take a look below the ground at the earthquake rupture that defines the seismic moment. That equation is then plugged into the moment magnitude equation, which is used by seismologists to measure the size of earthquakes in terms of the energy released, not just the amplitude of the recorded waves. The constants in the moment magnitude scale are chosen such that at smaller magnitudes, the moment magnitude matches the Richter scale. To truly appreciate this, consider the changes in the earthquake rupture required to increase the moment magnitude by 1 unit. Either the area of rupture or the slip distance, or both, must increase so that the product of slip distance times area increases by a factor of 32. While the amplitude of shaking caused by a magnitude 5 earthquake is 10 times larger than for a magnitude 4 earthquake, the energy released increases by about 32 times for each unit increase in magnitude. To understand the scaling, we'll look at the effects of the rupture area by using pasta as a model for magnitude. The cross-sectional area of a strand of spaghetti is about 1 square millimeter. When you break the noodle, it makes an earthquake of, let's just say, magnitude 5 for our model. Mu is constant for all strands of pasta, and for D, we'll use 1 millimeter of displacement across the fault. So here we see the pasta break and move laterally 1 millimeter. To increase it to a moment magnitude of 6, we multiply it times 32. The surface area is 32 times higher, yet the amplitude is just 10 times higher. To reach a magnitude 7, you have to multiply 32 times 32, and and you get roughly 1,000 strands, or about a pound of spaghetti noodles. To get a magnitude 8, you need 32,000 pieces of spaghetti. A magnitude 9, on the other hand, would require 1,000,000 pieces of spaghetti. A magnitude 9 releases 1,000 times more energy than a magnitude 7 earthquake.
Magnitude versus intensity. So let's start with a definition of magnitude and intensity. Magnitude is a common term used in geology to describe the actual size of an earthquake. Ito ay ang sukat ng enerhiya ng lindol mula sa focus, while the intensity measures the strength of the earthquake in terms of the actual shaking of the ground due to the earthquake. Ito ay ang lakas ng lindol na nadarama o nakikita ng mga tao at hayop depende kung saang lokasyon sila naroroon. Then, nasusukat ang magnitude sa pamamagitan ng seismograph. A seismograph is a device that produces waves or lines on a sheet of paper when the ground on which it is placed begins to shake. Sa kabilang banda naman ay ang intensity ay binabase sa pakiramdam ng tao at epekto nito sa paligid. Habang papalayo ng lugar mula sa epicenter, pahina ng pahina ang nararamdamang intensity o pagyanig. Sunod dito ay ang the magnitude is represented as a single number on the Richter scale. It describes the Earth's magnitude by measuring the seismic waves that cause the earthquake, while the intensity value is represented as a Roman numeral on the modified Mercalli Intensity Scale or the MMI scale. It describes the intensity of an earthquake based on its observed effects. Then, the magnitude value calculates the radius of impact of an earthquake, while ang intensity values ay ginagamit sa design calculations ng mga tulay, building at iba pang structures. An increase in magnitude level indicates a 10 times stronger earthquake. The intensity level decreases from the epicenter of the earthquake. Tandaan na hindi nagbabago ang magnitude ng isang lindol mula sa epicenter. Samantala, ang intensity ay nag-iiba-iba depende sa lokasyon. Mas malapit sa epicenter, mas mataas ang intensity. So, para mas palinawan tayo, ipanoodin natin ang video sa sunod na slide.
Magnitude and intensity are both related to the size of an earthquake, but they each measure different aspects. Magnitude, which measures the energy released at the source of the earthquake rupture and is calculated using measurements from seismic instruments, is one single value. Seismic intensity, which is the measurement of the strength of shaking at a specific location, determined from effects on people, human structures, and the natural environment, produces a range of shaking intensities in different locations. Thus, unlike earthquake magnitude, which is the same for all locations, the seismic intensity you feel depends on where you are. Intensity is mostly controlled by three factors: magnitude, how big the earthquake was; distance from the hypocenter, intensity varies from place to place; and the local rock and soil conditions. Let's compare magnitude and intensity by using a light bulb as an analogy. The light bulb represents the location within the Earth called the hypocenter, where the earthquake begins. The magnitude or size of an earthquake is like the wattage of a light bulb. Just as the wattage represents the amount of power of the light bulb, the magnitude is related to the total amount of energy released by the earthquake's source. The intensity, or shaking level, is like the amount of light from a light bulb at any spot in a room. A small light bulb in one area of a room will make that area bright with high-intensity light, but it will leave the distant areas of the room dim with low-intensity light. So, a given earthquake has only one magnitude, but will produce different intensities of ground shaking, as shown on the USGS Did You Feel It intensity maps.
To conclude, earthquake is one of the worst natural calamities known to mankind. It can result in devastating damages to both material properties and human lives. The impact of the earthquake is measured using the several factors. Two of those factors are the magnitude and intensity. Comparison between the magnitude and intensity are fraught with difficulty. First, intensity varies with the distance from the epicenter. Second, a large earthquake may occur away from inhabited areas and therefore cause little apparent damage. Although they are separate aspects, they are related in terms of impact produced by the shaking. Both factors together determine the damage caused by the earthquake.
So, okay na po